Let's distinguish between statistical and practical significance. In this lecture, we're going to dive deeper into what statistical significance means versus practical significance and why both are important to consider. So we'll start with an overview of both, and then we'll move in and dive deeper into statistical significance and finish up with a deep dive into practical significance. So let's start with an overview. So both statistical significance and practical significance are important to consider when evaluating the associations or differences between variables. Now, statistical significance addresses whether a hypothesized association or difference exists in the underlying population, whereas practical significance addresses the size of an association or a difference, or in other words, the magnitude or the meaningfulness of that association or difference given a particular context. Now, in many cases, we would typically only interpret practical significance if we found statistical significance for that particular association or difference. So let's deep dive into statistical significance. So statistical significance, as we just covered, addresses whether a hypothesized association or difference exists in the underlying population. Because remember, this is just for a sample that we're deriving a particular statistical significance test, and the sample comes from a broader population. So how do we determine whether an association or a difference is statistically significant? Well, the traditional or Fisherian or frequentist approach involves using null hypothesis significance testing, and this is quite common. However, I'd also like to note that there's also Bayesian approaches that can be used as well. Now, this can be kind of a contentious area in terms of using null hypothesis significance testing. It's by no means the best necessarily way of assessing statistical significance, but it is very logical in terms of the way that it's applied, and it's very much conventional at this point. But there has been growing murmurs about whether or not there is a better approach, and if so, what that better approach might actually be. And this can be quite controversial amongst different groups of statisticians. So let's distinguish now between descriptive and inferential statistics. And so descriptive statistics describe the sample as it is, whereas inferential statistics are actually used to infer something about the underlying population from the sample. And so when we evaluate statistical significance, we are making an inference about an association or difference of interest with respect to the underlying population value or parameter. And we are then conducting inferential statistics if this is the case. And so this is really what statistical significance is all about, is making inferences, hence inferential statistics, about the underlying population based on the sample data that you acquired or obtained. So inferential statistics are valuable because the results of a given study are based on data obtained from a single sample often. And for this reason, there's a number of things we need to account for, like sampling error, measurement error, and so forth. Further, data are often not based on an entire population of scores, because often the reason that we're picking a sample is that it's not feasible or even possible to get data from every single person or case from the underlying population. Further, as I mentioned a second ago, there's always going to be some kind of error, whether that's measurement error or sampling error. And so inferential statistics are used to determine the probability that an individual study result that we find or observe match what would happen if we were to conduct the study again and again with many samples in order to approximate what we would find in the underlying population. So in terms of making inferences about a population, again, we do that using a sample. And our goal is to get a representative sample of cases from that underlying population, or representative sample of data or observations from those cases from that underlying population. And so a particular statistic or a test statistic is going to be based on just one sample. And then we must infer whether that test statistic reflects the true population value or parameter. Now, population you can think of as being the sample plus any random error, which is sampling error in many cases. So sampling error being the extent to which the sample of people that we gather data on don't actually represent completely accurately the underlying population. So any kind of inferences we make about such a sample where there is sampling error, and there's almost always going to be sampling error, is going to affect the confidence we have in the inferences we're making. So now let's talk about what null hypothesis significance testing even means. And so as the name implies, there's a null hypothesis. And really there's two hypotheses. And it's actually usually when we're talking in a colloquial sense, we're not actually interested in the null hypothesis. We're typically interested in what's called the research hypothesis. So the null hypothesis is typically that there's no association or no difference between two variables or sets of scores or whatever the case might be. So for example, the null hypothesis might be that there is no association between job satisfaction and job performance, or another example, there is no difference between the test means for the treatment and the control groups, if we're talking about a training evaluation design where we have one independent group of people that went through a treatment group with the new training and another group that went through the control group or a comparison group that didn't receive that new training, and then assessing them afterwards on the same type of test and seeing whether or not their means respectively are different from one another. Now, the corresponding research hypotheses, where a research hypothesis is really describing that there is association between the two variables and that it actually exists, the corresponding research hypothesis for those two null hypotheses would be as follows. First, there is an association between job satisfaction and job performance, whereas the null hypothesis was that there is no association or zero association between job satisfaction and job performance. Now, regarding that second research hypothesis, there is a difference between the test means for the treatment and the control groups as opposed to the corresponding null hypothesis that stated there is no difference between the test means for the treatment and control groups. Now, we use a test statistic and the associated significance value, which is a p-value, to decide whether to reject or fail to reject a null hypothesis. Or in other words, in our traditional null hypothesis significance testing, we don't directly test the research hypothesis. Rather, we're determining whether or not there's evidence to reject or alternatively fail to reject that null hypothesis. So if we reject the null hypothesis, it's essentially the same as saying there is a statistical association or a statistically significant association or a statistically significant difference, whereas failing to reject would be essentially staying with that null hypothesis that there is, in fact, we don't have evidence that there is a difference or that there is an association between these two variables. It doesn't mean that it doesn't exist, it just means that we didn't find this in this particular sample. Okay, so let's talk about that p-value in a little bit more detail. So the p-value stands for probability value. So we calculate the p-value to determine whether to reject or fail to reject that null hypothesis, and in most cases our goal is going to be to reject the null hypothesis, and essentially implying that maybe there's some validity to that research hypothesis that we're ultimately interested in. So the p-value represents the probability of observing an association or difference in your sample given the null hypothesis is true. Or in other words, the p-value represents the likelihood that the difference you found in your sample was in fact due to chance or random error and does not in fact actually exist in the population. So let's talk about an example here where we'll interpret this example using two different levels, the technical interpretation and then the more colloquial interpretation of the same finding. Now, the technical interpretation is going to be in line with how a statistician would interpret it. The colloquial interpretation is more in line with how you might explain this to someone else. So let's think of this example. When testing the null hypothesis that two particular means are equal, we find, or in other words, that there's no difference between these two means or zero difference between these two means, we find a p-value of 0.03. In other words, p is equal to 0.03, and let's say our alpha cutoff is the conventional 0.05, which in this case doesn't matter so much, but let's just assume that that's the case. Now, in terms of the technical interpretation of this example, what we're really saying here, if you were to talk to and explain this to a statistician, you would say, if the null hypothesis were true, the probability of obtaining the difference between means as large as the difference we found is only 0.03. In other words, there's a very low probability. Now, the colloquial interpretation, how you might describe this to a friend or a stakeholder for this, would be that there is a low probability that the difference we found in our sample was due to chance. Now, the colloquial interpretation is not exactly accurate, but it's typically how we talk about this in everyday language. So how do we determine the probability cutoff associated with a p-value? Well, that's where that alpha value I just mentioned a second ago comes into play. So we set the alpha level, which represents the probability cutoff required for statistical significance. Now, conventionally, we use an alpha set to 0.05, and that's typically what we refer to as a two-tailed test, as opposed to a one-tailed test, at least for most of our purposes. Now, essentially, when we set the alpha at 0.05, what we're saying is that there's a 5% or lower chance that the difference, effect, or association we're interested in, or that we found, was due to random error in our one sample that we collected data from that was from the broader population. Now, for our purposes, we will consider the association again, or difference, to be statistically significant if that alpha level is set to 0.05, or in other words, if the p-value is less than that alpha level of 0.05, we're going to conclude that that finding is statistically significant, or in other words, that we would reject the null hypothesis, whatever that might be in that particular context. So, when it comes to statistical significance, we also need to consider the fact that we're not always going to make the right decision based on our p-values sometimes, and there are going to be certain errors that we make. And we can really distinguish between two sets of errors, which are referred to as false positives or type 1 error, or false negatives, which is sometimes referred to as type 2 error. So false positives or type 1 error refers to when we reject the null hypothesis based on a p-value being below that alpha level of 0.05, but the null hypothesis is actually true. So in other words, there really isn't association or difference between these two variables in the underlying population. However, we falsely concluded that there is based on our p-value because we decided to reject the null hypothesis. And this might be because of sampling error or because of measurement error or some other type of error. Now, so what is a false negative or type 2 error? When we're talking about a false negative or type 2 error, we're talking about instances in which we fail to reject the null hypothesis, but the null hypothesis is actually false. So in other words, we conclude based on the p-value that, well, it's greater than or equal to this alpha level of 0.05, let's say, and therefore we're going to conclude that, well, there's really no evidence of an association or a difference here, and so therefore we are going to fail to reject the null hypothesis. But in actuality, in the underlying population from which the sample of people are from, or the sample of cases are from, and their data, this is actually false. That there is actually a relationship between these two variables or a difference between these two sets of scores or whatever the case might be. And so false positive, or rather a false negative or type 2 error is essentially failing to find something that actually exists in real life. Whereas a false positive or type 1 error is claiming that you found something that doesn't actually exist in reality. And so these both can be problematic, and you really have to weigh these. And anytime you try to reduce the amount of type 1 error you make, you're actually going to increase the potential for type 2 error. And anytime you try to decrease the amount of type 2 errors you make, you're actually going to increase the amount of type 1 error. So it's this give and take that we have to do. It's beyond the scope of this lecture of why that occurs, but if you learn more about power analysis, this will explain why these are inextricably linked. Now, the ingredients when it comes to this concept of statistical power really have to do with the ideas of what you set your alpha level at. That's going to affect those error rates and the types of errors you make. And also your sample size, where generally the larger your sample size is, the fewer errors that you're going to make. And then finally, your effect size. So typically where it's going to be easier to detect effects that are larger compared to those effects that are smaller. So larger effects are typically easier to find. Now, again, this idea of statistical power, this is going to be related to this idea of how confident we can be in the results that we found, that we actually made the right decision based on the data and the underlying population from which those data come from. And so really statistical power is related to this idea of the likelihood that we make various errors. So now let's move on and talk about something that's very much related to statistical significance. In fact, it's just another way of looking at it. It's this idea of what are referred to as confidence intervals. So we've discussed a p-value, and a p-value is associated with the sample-derived point estimate, such as a t-value, an f-value, an r-value, from an underlying population. So by point estimate, we simply mean we find an R value or a correlation value of, let's say, 0.32. Well, in that case, that is a point estimate. That's a very specific evidence there. That's not estimate, that's not an interval. Well, in contrast, a confidence interval, which is sometimes abbreviated just as CI, provides a range of values that likely contains an unknown population parameter. In other words, it represents the margin of error around that point estimate that we derive from our sample. And so this can be really useful sometimes in terms of understanding things in terms of a confidence interval, because it can give us a better idea in practical terms what we're actually talking about and how much confidence, or in other words, how much margin of error do we have to contend with when it comes to our estimation. where a small confidence interval will give us more confidence, whereas a very large confidence interval or a wide confidence interval will give us less confidence that what we found in terms of the point value is close to the actual population value. Now, let's assume with a confidence interval that we can also use the corresponding alpha value or alpha level that we set with our p-value. So the equivalent of setting an alpha value to 0.05 for the cutoff for statistical significance for that p-value is going to be to select a 95% confidence interval. Likewise, if we were to select or use alpha level set to, let's say, 0.10, so 0.10, then the corresponding confidence interval would be a 90% confidence interval. Alternatively, if we were to set our alpha level to 0.01 for testing that statistical significance as corresponded to our p-value for the point estimate, 0.01 alpha level would correspond to a 99% confidence interval. And so it's really a matter of how liberal or conservative we want to be in terms of forming these intervals. Now, if the lower and the upper bounds of a confidence interval do not include the null hypothesis value, which in many cases that we're interested in is going to be 0, then we would conclude that the association or the difference is statistically significant. Now, if that lower and upper bounds of that confidence interval does include 0, then we would conclude that, in fact, there is no association or difference that we could find, at least based on the alpha level that we set and the corresponding confidence interval. So let's think of an example here. So when testing the null hypothesis that two means are equal, let's assume that we find the following 95% confidence interval of the mean difference: 6.41 to 15.67. So exactly in the middle of that interval there of 6.41 to 15.67 is going to be whatever sample-derived point estimate we came up with and that we would have used to then assess whether or not use the p-value against or with to determine whether or not that is statistically significantly different from 0. Now, we have the technical interpretation of what this means, and this is the interpretation a statistician would give you, and that is that the confidence interval of 6.41 to 15.67 from the sample either contains or does not contain the true mean difference. So it really is just kind of this yes or no binary here. Does contain or does not contain the true mean difference from that population in that interval of 6.41 to 15.67. That's not terribly intuitive or interpretable by itself, but it is important to recognize that's actually what we're saying here. Now, in terms of a colloquial interpretation, and statisticians might jump on you for this if you say it this way, but many people wouldn't fault you necessarily for trying to explain it in these ways to different stakeholders and groups of people that don't understand what's happening behind the scenes here. If you were going to explain it to such people that are not statisticians, you would describe it as follows. There is a probability of 0.95 that the confidence interval ranging from 6.41 to 15.67 contains the true mean difference. So in other words, that whatever the true mean difference is in the underlying population, that is going to fall somewhere in the middle of that confidence interval there, and there's a 0.95 probability that that's the case. Okay, so again, that's the colloquial interpretation. Not technically how you should describe it, but that is something that many people would kind of give you room to fudge things a little bit and have a little wiggle room to describe it in a way that's a little bit more interpretable than the more statistics and technical interpretation of it. Okay, so now let's move from statistical significance to practical significance. Okay, so if you recall, practical significance addresses the size of an association or a difference, whereas statistical significance is about whether or not an association or a difference seems to exist given the data that we have. Now, in many cases, we only interpret practical significance if we find statistical significance. So we wouldn't interpret practical significance unless we find that there's evidence that an association or a difference actually exists. Now, an association or difference might be statistically significant, but that also doesn't mean that it exhibits a meaningful or substantial effect, and that's why practical significance is important to consider. So you might have a really what we would call overpowered study in terms of statistical power, where you're able to detect even the slightest differences and find those to be statistically significant. Now, are those meaningful differences? Well, maybe not, and that's why practical significance is the other thing that you need to consider when you do have statistically significant result. So effect size is very much inextricably linked to this concept of practical significance, where effect sizes can be used as indicators of practical significance. So an effect size is an index of the quantitative relationship between variables. It's standardized such that you can compare effect sizes from one sample with that same type of effect size from another sample. And so for this reason, we can start describing the size of the effects in qualitative terms like small, medium, large, or weak, moderate, strong. Now, examples of effect sizes include, but are not limited to, Cohen's d, Cohen's f, correlation coefficient represented by r, an r-squared value, which is variance explained, or even an odds ratio. So when we describe the effect sizes qualitatively using different rules of thumb, we can use some, such as those that were provided by Cohen. We can come up with these more or less good rules of thumb. These aren't really context specific, and so you'd want to, in your organization and in whatever particular context you're applying these, think about what would be the most meaningful cutoffs to qualitatively describe your findings in terms of practical significance and the effect sizes you have. But if you don't have anything else, these are a great starting point. So let's start with the fact that we're going to describe these very coarsely as effects are either small, medium, or large. And so small effects are around whatever values I'm going to give. Medium are around whatever values I give you for medium, and large are around whatever values that are given for large. Now, they don't have to be exactly that value, but just kind of ballpark in that range. So with a correlation coefficient, a small effect would be 0.10, a medium effect would be 0.30, and a large effect would be 0.50, at least in the context of social science data or data involving people. Now, an r-squared value, a small would be 0.01, a medium would be 0.09, and a large would be 0.25. Eta squared and omega squared will be interpreted in the same way. Now, in terms of Cohen's d, which is the standardized mean difference, a small would be 0.20, a medium would be 0.50, and a large would be 0.80. Cohen's f, on the other hand, which is associated with an omnibus f-test for an analysis of variance, a small would be 0.10, a medium would be 0.25, and a large would be 0.40. And then finally, with an odds ratio, a small might be 1.5, a medium might be 3.5, and a large might be 9.0. So to sum up, in this lecture, we distinguish between statistical significance and practical significance. As I just was chatting about, this idea of practical significance is very much linked to the notion of an effect size. And so remember, if you do find that something's statistically significant, whatever association or difference that might be, don't just stop there. You need to also interpret, well, in practical terms, or in terms of practical significance, how meaningful is that association or difference? How much should we care about it? How much should we invest in that? How much should we chase after that and learn more about it? This is really going to help you allocate your resources if you think in terms of both statistical and practical significance. So this wraps up the lecture in which we distinguish between statistical and practical significance. Thank you.